Okay, we are recording now, so you can start.
Yeah. So hello everyone, and welcome to our session today. I'll be doing a workshop called Astronomy Toolkit. You probably need to mute some people. Hello. Yeah.
Yes.
Yeah. Can you hear me clearly? Hello. Can you hear me clearly?
Yes, we can listen to you.
Okay.
We
Okay.
can.
You just stop me in case there's a problem. Okay. Okay. Fine. So, hello everyone, and I am Dr. Priya Hassan from Maulana Azad National Urdu University in India. And what I'm presenting to you is a workshop which is entitled Astronomy Toolkit 1.0. And essentially, the purpose of this workshop is basically to provide you some basic skills which are necessary in today's times for research in astronomy. And I will be doing some sessions to you with you today, as well as a hands-on session tomorrow, rather day after tomorrow, where I will actually describe these things more in detail. Right? So the first session today, I'll be describing Virtual Observatory and its tools, and how does it get integrated with the Astrophysics Data System. And we'll talk about a little bit of the softwares, etc. used. And the next session, which I'll be having on the 22nd, that's when I'll be doing a hands-on session on the actual usage of VO tools. I will do one with Gaia, and then if there's time, we'll also probably do something with HST or SDSS data, depending on our time and how it would do. And what I today there would be lesser hands-on. Next time it would be completely hands-on. But in case you have any doubts or any questions, I would be happy to answer your questions at any time. So please do not hesitate in interrupting me in case you have any questions. So, like I mentioned, we are trying. What I'm trying to do is typically for an observational astronomer, what are the kind of skills you would need if you want to have a research in astronomical data? Now we know we live in an era of multi-wavelength data where there are various ground-based and space-based surveys which range all the way from gamma rays, X-rays, ultraviolet, optical, infrared, radio bands. It covers the whole of astronomy, the whole spectrum, right? And astronomical data is already amounting to petabytes, and it's increasing with the advent of new instruments. So now, what happens with astronomy? Earlier, when people studied it, it was done on what was called the hypothesis-driven, where you actually make a hypothesis, and based on that, you make observations and try to study whether your observations agree with your hypothesis. But in today's times, because we have so much of data, there's so much of data, it's a data rich science. So now the kind of research we do is more than hypothesis driven, it is data driven. In the sense, we have some results which we get from data, and we have to interpret those results to actually give us some meaningful science, right? So just to give you an example of the kind of data volume we are using, if you see the older things, the DPOS survey, that's the Digital Palomar Sky Survey, it just had about 3 terabytes of data. The TUMA State Survey is 10 terabytes of data. The Galaxy Survey is 30 terabytes. But the Sloan Digital Sky Survey is 40. But now, the new observatories which are coming in, for example, what you can look on this upper right, this is the Vera Rubin Observatory, which will do the LSST survey, the Large Synoptic Sky Survey. You can see that this is going to give you 14 terabytes per day. Okay, so it's every day it's going to give you something of a factor of what these other databases were. Similarly, the SKA, all these data sets are going to give you a lot of data. Now, data, the way we've been handling data or the net has been, developing very fast over time. So if you see the internet, the earliest usage is something like the 1960s. By 1970s, emails had started. By 1980s, we had the World Wide Web at CERN. In the 90s, you had web browsers. By 2000, people realized that there has to be some kind of a concept of data access, interoperability between data. And then by 2010, people already started considering how could data be used in society in interoperability projects. And there was this new concept of fair data. where you have data which is findable, accessible, and usable by everyone, right? And astronomers have been always very early adapters of these developments. So, as these developments came in, obviously, email was immediately adopted. By the 1980s, we had data services on the net, which included the NASA Extragalactic Database, which is called NED, the SIMBAD database, and they already gotten the idea of having FITS files. I'll talk about that in a bit. And soon we already had the astronomy astrophysics data service at the Smithsonian Astrophysical Observatory, which gave literature access, data access, etc. And by the year 2000, we had the conception of the virtual observatory. Now you already have a lot more virtual observatory initiatives, and even the UN is now working with what is called the open universe, where they are trying to open data to even non-astronomers, to the whole community of people. And therefore, now the International Virtual Observatory Alliance, or the IVOA, actually integrates the International Astronomical Union with the United Nations, where they are all looking for already peaceful uses of outer space and using of the virtual observatory. But let us define what exactly is the virtual observatory. So, like I mentioned earlier, astronomy involves observations of the universe in various wavelengths, right? From radio and various wavelengths, X-ray, gamma ray, infrared, etc. And what we basically want to do in today's time is that the multi-wavelength data of the digital sky, we should be able to search it, visualize it, and analyze it in new and innovative ways. So, for example, if you are looking at a certain galaxy, you should be able to look at the galaxy in various wavelengths and in various kinds of ways, right? So, what Virtual Observatory does is it actually creates what are called data centers. Data centers are places where data is sitting, right, in a certain file structure. And these are actually defined by the Virtual Observatory. In the sense, the Virtual Observatory defines as to what is the format in which you're actually going to be putting your data, right? It actually puts what are called standards, Virtual Observatory standards, so that data is stored in a certain way so that people can access it and use it for their requirement. They also use the FITS data, which is the flexible image transport system, which is also standardized. And therefore, this actually gives you a natural progression where you can have an interoperability or exchange of data, services, as well as tools, right? So, in principle, you can already think of it as a framework in which you have data archives, which can organize access to astronomical data holdings in commonly agreed shared data structures. You have software provided to actually do data analysis, and the data centers which actually cooperate to provide the data services. So, the International Virtual Observatory Alliance was actually formed in 2002, 20 years ago, with the mission of actually facilitating this international coordination and collaboration necessary for this exchange of data, as well as setting up standards of data and exchange, right? Now, the virtual observatory, it actually is self-funded, so it comprises 21 VO projects. So, what you can see over here, these are all country-wise different VO projects. So, for example, the Indian one is called the VOI. There is the Spanish Virtual Observatory, the European the German one is called GAVO. There's the Japanese one, the American one, the NVO, the Euro VO, etc. So, but the thing is that all of them are self-funded. They have to get their funds on their own, but they work together to develop the virtual observatory. So essentially, you have the virtual observatory, which has working groups, which deals with the data of how to organize the data. And you have interest groups, which actually focus on certain interests. I'm not going to talk too much about it, but this is just to give you a broad idea. So let us move on to astronomical data. What is astronomical data? Astronomical data can be of various formats. The first thing could be an image, okay, an astronomical image. You could also have what are called catalogues. Catalogues are tables, tabular data of certain variables or certain parameters. Data could be also in the form of spectra, where spectra are, reduced or in a certain format. Or you could also have some kind of polarization data, and you could also have a time series data. I should have mentioned that. You can also have a time series data. But what is the format in which astronomical images are stored? They are essentially XY grids, right? A 2D array where you have a certain count for a pixel value. So you have this 2D array where you have a certain count for a pixel, and based on that, you make the image. And if you want to have colored images, RGB images, you will have to add on images which are observed in different filters. So and the images could be either of point sources or extended sources. Point sources, for example, stars. Extended sources, for example, galaxies. So here we have a picture of Boyle and Smith. These are the two people who actually invented charged coupled devices. Now, charged coupled devices got a major revolution in astronomy, which basically got us what are called digital images in astronomy. What is a digital image in astronomy? Okay, this is a digital image in astronomy. Like I told you, you have an XY grid, and on each point you have a certain count, okay, a certain number which describes the brightness. So typically what is done in astronomy is you have this image over here. We put different kinds of filters. So your filter could be red, it could be green, it could be blue, and depending on the light which falls on it, you will activate you will activate certain, these are called pixels or picture elements, where you will get a certain count. So, for example, the red light will give a count of red pixels, the green one will give it for green, the blue will give it for blue. And when these things add up together, they actually give you a colored image. So, this is exactly how you get a colored image, for example, in your digital cameras, in your camcorders, in scanners. This is exactly how you get color images by using this kind of a thing, a grid with various colored pixels. This is how it is in your camera. But in astronomy, what we do is something different. In astronomy, we use different filters and we get a red image, a green image, and a blue image. And we add up all these images to actually get the colored image, right? So here's the astronomy example. Like I said, you use filters in succession. You use, supposing the blue, the V, supposing you're using UBV filters. So U is an ultraviolet, blue is blue, and V is visual. So what you will do is you'll take the image in all three filters, and then you will add them up to create what is called an RGB image, which you can see over here. Often in astronomy, we also use artificial colors to actually enhance images. And images are stored in a certain format, which is called the FITS format. The FITS is the Flexible Image Transport System. And basically, it is the format in which we store astronomy images. In FITS, we also have what are called headers. A header is an attached thing with the image, which actually has information about the image. For example, where was it observed from, which telescope, what is the size of the image, what's the filter, what's the exposure time. This is all metadata of the image, which sits with the FITS image. Now, the brightness, like I told you, the brightness is scaled in different ways. Supposing you have a 16-bit image, machine. In that case, the brightness count can vary as 2 power 16, which is 65,536. So if I have this is the image, you can't see it very well. This is what is called, this is an image with what is called linear scaling. That means you just take the count and you take a linear scale. But if, for example, we could make a break in the linear scaling, in the sense we make it, for example, for 4572 to 6002. That means supposing if the counts that we all had lied within the range 4572 and 6002, then you would get an image like this. If I further square the scaling, I can get an image like this. So what we do in astronomy often is that we kind of play with our image. Supposing this is your image, you may enhance the image by doing things like this. I will show you in a bit how do we actually do that in person, but just give me a minute. So here, let us look at this image. This is an image, this is called the Pac-Man Nebula, where you have this cluster. You can see that there is a red part and there's a purple part, right? And why do I have the red part? This object has been observed using Spitzer, and Spitzer is an infrared telescope. And you can see that there is a further image, the square, the blue square, the big one. This is an image which is with Chandra, which is an X-ray telescope. The cyan image is Spitzer, the original Spitzer. And then when we had what is called the warm Spitzer, we got the outer image. So now when I take these images in different wavelengths, I can add them up. So this is the X-ray image. I had the infrared image, right? And I can add these up together to give me this kind of an image, right? So in astronomy, we can add up these images. So the red part is from the infrared image and the purple part is from the X-ray image, right? And the data can also be, like I mentioned, spectra. What are spectra? Is you have intensity versus wavelength, and you will have a certain brightness. So you could have the spectra given to you as an image where you have this kind. Can also be in tabular form, where you actually have tables for the spectra, which give you the intensity at different wavelengths, right? Um, you could also have what are called data cubes. That means supposing you have this image and you have it in different wavelengths. Let's say I have the image in blue wavelengths and green and in red. I can stack up these images together to give me this thing. Or for example, if I use integral field spectroscopy, right? Then I can have each pixel can have the spectrum received. And therefore, if you look at it along this axis, you can get the spectrum for every pixel, right? And these are what are called data cubes. So we can have data in the form of data cubes. Here you have a mixed image. The other way in which we can have data is what is called catalog data. That means here you see I have a table. I have a table where I say, for example, I have a cluster name. I have the right ascension, the declination, longitude, latitude, and various other parameters. And this is in form of a table. So I can observe this table using something called TopCat, which we will talk about in a bit. And you can actually see this kind of tabular data. You could also have data in the form of a time series where you have time and you have, for example, this is your time and this is your brightness. So you can see the variation in brightness with this time in the form of a table. So this is what is called time series data. This is typically the kind of data you get when you're doing variable sources. For example, if you're studying exoplanets and you were seeing the data which, say, for example, you are getting from Kepler, you will get it of this format where you'll get a variation in the brightness, right? So this is the different kind of data which you have. Now, the next important job of Virtual Observatory is to give you tools with which you can see this data. So we are going to see very soon a tool called DS9, which is used to visualize images. If you want to see an image, you can see the image using something called DS9, which is Deep Space Nine. If you have catalogs, you can see the catalogs using a certain thing called TopCat, okay, for catalogs. It also gives you certain programming languages, modules. We'll also do something called Aladin, which is also used for this thing. You can have various metadata for this thing, which we'll talk about later. So how is all this data placed? There is something called CDS, which is the Center of Data, which is in Strasbourg. And I will show you these various things. I will show you Simbad, I will show you Vizier, and I will show you Aladin. This is where all this data is actually kept, right? But we'll talk about it in a bit. So it gives you, CDS gives you access to the data. And you'll see that this data, it actually is called the Astronomical Data Center. And you can access various things ranging from catalogs to papers, etc. So Simbad is something which I'll just show it to you in a hands-on thing. This actually gives you data on 12 million objects, almost 13 million objects with certain identifiers, and you can get data on these objects. We'll just see it in a bit. Vizier is a way of actually looking at catalogs, which I will show that to you, which is hosted by CDS. And Aladin is a visualization tool, which we will also see in a short while. Virtual Observatory also provides various statistical packages other than the ones available, which will help you to analyze data. For example, you can use the R package, which is a package for statistics. So you can use that in a thing called VOStat. There are various VO tools, which I will show you in a bit. So like I said, R is a free software which is available to do basic statistics on data. So you can actually use this, and it is accessed using something called VOStat. So VOStat is a statistical analysis package of the Virtual Observatory. This is just a front end of R. So it basically uses the R statistical package, but uses the certain front end called VOStat. And you can use this to actually do some basic statistics on your data. It looks something like this. I will show it to you in a bit. And you can actually upload your data and do certain tests, right? There's another tool also in Virtual Observatory, which is called VOplot. So that means if you have data, you can plot the data using VOplot and make various plots like this. So you can make from VOstat, you can make plots like this, which look like this. And this is essentially VOplot. VOplot gives you plots like this, where you have a drop down menu and you can choose things and in a very easy manner make plots. All right, with various projections. These are just some examples of some plots which you can do with VOplot. There's also something called Vocat, which is a standalone tool which is used to convert astronomical catalogs to MySQL databases. And this can be used typically if you want to use a very large data set, right? And I'll soon show you the demo. But before that, we will talk a little bit about the astrophysics data set. Okay. So let me stop sharing this thing. And I will now start off with some kind of a, I will start on with some kind of a hands-on session where I will actually show you. Okay. So I hope all of you all can see my browser, right? I hope you can see my browser. Hello? Yeah. So the first important thing, I
Yes,
hope you can see my browser, right?
Yes.
Yeah, great. So let us first start off with astronomy visualization tools. So like I mentioned, the simplest visualization tool used in astronomy is called DS9. So if you all are sitting with your laptops, please use your browser and look for DS9 and say enter. Okay, this obviously gives you Star Trek. So let us instead say DS9 astronomy. That's not a surprise because it was actually named Deep Space Nine essentially from Star Trek, but this is the name of the tool that we use, right? So this is DS9, which is the tool which we will use for this, or let me call it SAO image, right? So the first name which given for it is SAO image, right? So I won't use, let me use SAO image instead. I want to go to the website. Yeah. So if you go into this, we can actually download the SAO image. So you can say SAO image astronomy, download. Most of these tools are very simple to download because they are not they are not OS dependent. Most of them are Java based, and therefore you will not have a problem in downloading it, right? So depending upon the system you are using, if you are using a Mac, for example, you'll say download SAO image for Mac, right? This is the DS9 for Mac, and you would download it from here, right? uh, Depending upon, here's the download, this is the download button if you're using a Mac. In case you are using a Linux machine, you can go into this, and if you're using Windows, you can use what, right? So I can even say for Windows, I should have asked most of you what is the OS you are using, but you can use this and download it, right? So you'll go in for your free download and accordingly download, right? So once you have downloaded this, right, I'm using a Windows machine over here, and therefore I'm going to open it in Windows. And where's the S9? 1 minute. I'm sorry, this is not my machine, so I'm having a problem using this. Yes. 1 minute, I'm sorry. So if you've downloaded this thing, you should be able to open DS9. But I can't find it. 1 minute. I'm sorry. This is not my computer, so I'm having a problem with this. But the rest of you all can actually try downloading DS9. Acham, I can't find DS9. Okay, yeah. I hope you all can see my screen. And this is DS9, right? So I hope most of you all have managed to download this thing, right? I will look for the chat window. Since this is a workshop, we'll try to right. So please, in your chat, please let me know if you have managed to open the DS9, right? Now DS9, like I mentioned, it will help you open. So if you want to open an image, you will say open, and you've got to open the FITS file, right? So I'm opening a FITS file over here, which is this one, and I say open. Now, often if you open this FITS file, you may see that you're not getting anything, right? You can't see anything much over here in this file. And this is essentially because, like I told you, because of the scaling, right? So you have to actually adjust the scale. And generally, if you do scale, the linear scale, you can say is not giving to you. But if you go in for a log scale or a Z scale, you will see that you'll be able to actually see the objects over here. So you can even click on color and you can see this object better over here. So if you are using a mouse, you can actually press your mouse, the right
Sorry.
button,
Sorry.
and try to adjust it to get a better contrast. Yeah.
Yeah. Sorry to interrupt, but we can't see anything, just a screen in white.
Okay, then I'll just try to do it again. Sorry. I'll just, I'll try it again. I will do this window. Sorry. Can you now
Yes.
see the screen? Okay. So I
No,
hope
wait.
everybody, all of you all managed to get DS9.
Yes.
And here I have the image. I'll show you once again. You will say file and you say open. And you have to open a FITS image, right? Like I told you, the FITS is the data image in astronomy. And like I told you initially, when you open it, you may not be able to see anything much, essentially because if it's you have to click on scale, and if it's a linear scale, you won't be able to see much. But now I've already adjusted this, and therefore you can see this image over here. So typically, what is done with DS9 is we are looking at an image, right? And please, everybody, try to set the scale and adjust. If you use your right button on your mouse or even your scroll pad, you can adjust this contrast. This is what I'm actually doing. I'm using a scroll pad, the right button, and I'm adjusting this to get different brightnesses, right? I can even change my color map. You can say color, and you say for example, cool or rainbow or whatever. You can change these things. These are essentially done just to improve the contrast in an image so that you can see the image better, right? So it's the same image which you're observing, but with which you can put it like this, right? So I hope people have managed to use the SAO image. If you actually see over here, in the SAO image, you basically have what are called frames, right? So this is a frame. I can make another frame. This is one frame. Supposing I want to display another image, I can say new frame. And in the new frame, I can open another file. For example, of those two files, I'll open the second file and I can say open. And if I want to see both these images, I can click on file and I can say tile frames. So that will let me see both these. This is the first image and this one is the second image. So I can see both the images when I tile my frames, right? I can also click on frame and I can blink frames. In this case, both these frames are this. Okay. Yeah. So someone's asking, how can I actually get the images? So should have shown that to you. So let me do that. So I will just stop this thing. Let us. Okay. Let us go back to our browser and I can show you how do we actually get images. Okay. So right. So yeah. So for example, let us go into something called I think I told you about CDS. Let's go to CDS. CDS Strasbourg, right, is what you will write. CDS Strasbourg. So I'm sorry I jumped a bit. I should have shown you how to get an image, but we can go into CDS Strasbourg. Okay. And here, if we want to get images, we can get into Simbad. Okay. So please click on Simbad, get onto Simbad. All right. Okay. Now in Simbad, this is actually giving you various data about objects. And for example, if I want to do a basic search, I can do a search, for example, by what is called an identifier. So I can say by identifier, I'll have to give the name of an object. For example, let me write M31, right? M31 is a galaxy, which is Andromeda. So please type M and 31, right? And you can, I will slightly increase this thing. I'll do it at 20 arc minutes. I hope everybody is onto this website. Actually, I can share this website, the link to this website on the Google Meet chat. Where is the chat? Yeah, here's the chat. So in the chat, I've shared the link. 1 minute, I'll just share the link. I hope everybody can use the link which I've shared on the chat. And you can use that to go on to Simbad. Okay. Now you click on Submit ID. And now here you can see details about this object, right? So this is a galaxy M31, which you can see over here. And you can see there are various details given about this galaxy. Now this has actually been observed. It's telling you that this is a galaxy, right? Which has so and so coordinates. This is its right ascension, its declination. It's telling you its velocity. It's telling you that it has been observed in these filters UBV, JHK, and this is all the stuff about it. These are the references. This is the paper in which it was observed in UBV, and this is the paper in which it was observed in JHK bands, right? And here it tells you even more things about it. These are different names. The same object has different names in different catalogs. So it's M31 over here, but in IRAS, it has another This is an infrared catalog. It has another name. For example, if you see it in NGSC 224, the normal name which we call it is Andromeda Nebula. And these are the various references. Then it also tells us what are the measurements made with it, which are velocities, distances, etc. And various archives where you can actually get material about this, right? So you can get material about this in these various places, right? Which are mentioned over here. And so here you are getting data about this object, right? You can make various other inquiries about this. For example, let us go back to CDS, right? I can use another service of CDS, which is called Vizier. What does Vizier do? Vizier essentially, it actually looks for catalogs of published data, right? So it actually looks for publications which are about a certain object. So for example, if I want to look about publications about M31, so I can say M31, I can actually select which wavelength are we talking about, which wavelength, which mission, which this thing, and I can actually look for catalogs which are available on M31, right? So I can say look for this thing, and I actually Vizier will let me search that. So I say find. Oh, sorry, I can even share this address with you all on the chat window. This is the, I'm sharing the address with you for Vizier. Okay. This is the sharing for Vizier, right? So what I showed you before this, I'll just go back, is that I am looking for catalogs about Andromeda galaxy or this galaxy called M31. So I say find. And once I say find, this actually gives me a list of catalogs or data which is available on about M31, right? And you can see the list, which I've seen it in a minute, right? I hope all of you will are with me, and in case anybody is having a problem, please do let me know. Now, what you can see over here is these are various catalogs in which has been mentioned, but this is not that. It's a mix of all these other objects. So I will instead go back and I will instead search over here M31, and let me check this. This has given me right. So Vizier is basically letting me access published data, and so you can see that there are various things. For example, Chandra X-ray observations, or for example, here you can see M31 Herschel images. So I can click on this M31 Herschel images, right? And here you can see that these are catalogs. So what happens is, if you have these images, it is actually telling you the number of images, etc., which are there, and the details about it. So if I say submit, right? If I say submit, it actually shows me these details about this data. So I can click on this. If I click on this, okay, oh God, I should not do this because I cannot use this to actually, this is a FITS file. So I cannot use the browser to observe a FITS file. So I will have to download the file and get it if I want, right? Um, if I want that file, right? So I will have to download it. I can take it like this and download it, right? What Vizier also lets me do is when I observe things, you see I saw it in HTML format. I can actually see my results in an unlimited format, unlimited form in various formats. You can download these tables in a VO table format, in a FITS format, in various formats, right? And that's what you can do with the catalogs which you get with Vizier, right? Uh, Let us go back to CDS, and now you can see what we call Aladin. Aladin is the visualization software which is held by CDS, right? So what you all can do is I'm going to share this link with you, and you can actually download Aladin desktop on your machine. So I'm going to share this link with you on the Google chat for Aladin. Please take the link of Aladin here and download Aladin desktop on your machine, right? I'm going to preview this thing and show it to you, just to show you Aladin Light. Okay, but you all can all download that. Okay, please download Aladin. Here you can actually see images. I can say, for example, M31, right? And I can say enter. So what's going to happen is this is going to give me the image of M31. Okay. Let me open the other Aladin. I don't want the light. I'm just hello. Can you see my screen?
Yes, you disconnected from
Okay. That's what I was wondering. So at what point did I disconnect?
when you disconnected when you started to talk about the Aladin.
Okay, okay, fine. Then I'll just share that now. Okay. Yeah. Okay, so I'll just
Just
continue.
was just a few minutes. No,
Okay, no
no.
problem. No problem. So I hope all of you all have managed to download the Aladdin from the link I gave you in the chat window, right? I hope people have managed that. And here you will write M31. Okay. I hope everybody's trying this out. Okay. So this is the basic virtual observatory visualization software if you want to actually look at something, right? I hope everybody is with me. In case you have a problem, let me know. So I'm going to write M31 and you'll press enter. And here you can see this is my M31 Andromeda galaxy. I hope everybody can see it, right? Yeah, they can see it. Yeah. Okay. Right. Now, this is the visualization software which is provided by Virtual Observatory. You can zoom in and zoom out. You can see this is a bar over here with which you can zoom in and zoom out. So I have used this bar over here to zoom. You have various other buttons over here. For example, there's a pan button with which you can move. You can actually measure distances. For example, if I wanted to measure the diameter, I can draw a line over here, right, to measure the diameter. And you can see here I'm getting 2.6 degrees. So supposing if I wanted to measure the size of this galaxy, supposing I wanted to get the minor axis, this is the major axis. If I want the minor axis, let me draw it like this. And you can see I'm getting 29.99. So I'm getting 30, approximately 30 arc minutes is this, and this distance is this, right? Now you see that in Aladin, you actually have planes. So if I do something, if I switch this off, I can remove this plane, okay? But I can add planes with whatever I want, okay? So for example, I can also here click on Simbad, right? So Simbad will actually mark all my objects in the image for me, right? So if you look at this is Simbad, and you can see it's marked over here. It's marked everything over here. I will have to actually draw a thing where I mark this. And if you look down over here, this is giving me this list. For example, it's telling me that this is M31, which is a galaxy. You can see M32 is being given over here, which is this thing over here. And you can see all these objects are being described over here, right? So if there are any objects which you want to explain, you can see them from here, right? I think this clicked something wrong, right? So you can see over here that in this image, now you have too many things. You have too many things. So I will stop it, but you can see that you can use Simbad to identify everything you want onto your image. There are too many things, therefore I removed it, but you can do this. Similarly, you can change the image. You can see this is the image as it is in using the DSS image. I can also look at Andromeda Galaxy using a WISE image. So I can put WISE. If I click on WISE, it's going to show me the WISE image of this. And what Aladin does is you can see that it's giving me WISE. This is our DSS image. I can actually look at the image of this galaxy in various wavelengths, right? So I can also observe it in 2 mass if I want, which is near infrared. I can do it with WISE, right? I can do it, which is mid infrared. I can do it in various wavelengths, right? So you can go back to the DSS image if you wish and observe that. Or you can choose the WISE image if you want. You can just have to click on this and you can get various planes. So what Aladin actually, when you play around with it, you will see that there are many things you can do with it. You can actually overlay catalogs over this. If you want to put a catalog on this, you can overlay the catalog. Supposing if I'm using Gaia, I can click on Gaia and this will put the Gaia catalog for this object over here and actually mark all the objects using Gaia. So you can see that here, these are the Gaia catalog objects. And if you mark this over here, you will see over here, you have all these Gaia sources. Since it's Gaia data, you have RA, DEC, you have parallax, you have proper motion in RA, proper motion in DEC. So for each of these objects, you're going to get all this data, right? So this is the Gaia data for this object. And these will come into different planes, which you can use to do this, right? So that is Aladin. So essentially your homework for today is to install all these packages because we will be using them tomorrow. The next important thing I want you to install is something called TopCat. Okay, so please write TopCat. I will share the URL with you in the chat window. I will also share it with you in our Discord group, right? So this is TopCat. Sorry, this is Aladin. TopCat is coming here. So I'll give you TopCat. TopCat is the software which is used for visualization of tables. Okay. So I'm going to share this over here with you. TopCat. Right. So please everybody go onto this website. This is the website for TopCat. Like I told you, tool for operations on catalogs and tables. Scroll down, and here when you come to the part on, when you scroll down over here, you'll come to downloads, right? Like I told you, essentially, this is a Java file, right? And therefore, all you need to do is to download topcat full.jar, okay? That's the jar file you will do. If you have a Unix system, you will just have to, you will say java minus jar, topcat.jar. If you have a Mac system, if you have a Macintosh, you'll have to download the topcat full.dmg. And if you have a Windows system, you will have to download this one. All right. So depending on whatever is your OS, you will have to download the required TopCat. Okay. Once you download TopCat, I'm just giving you a brief view of it, but essentially you have to try to download it. And where is TopCat? Right. I'll just stop sharing, and I'll now share my TopCat.
Sorry for the interrupt, but I think yeah, that we were looking at the Aladin screen.
Yeah. No, now I'll open TopCat. I'll open TopCat. Yeah, 1 second. The problem is I moved to another system which is not mine, so I'm just opening it. 1 second. Okay, no problem. So I will just briefly show you what the TopCat screen looks like. I hope you can see my TopCat screen now. Okay, I hope you all can see my screen, right? The TopCat screen. Yes. Yeah. So if you the TopCat is the VO tool which is used for data. Okay. So what we can do is we are going to download some data, and we will then view it, right? So please click on VO, Virtual Observatory. Okay. Please click on VO, and let's go do what is called a cone search. Okay. Click on cone search. Now, we'll just be looking at, we have a little while left. So I just want to show you, we'll just look at some Gaia data. So please type Gaia EDR3. Okay. That is the early data release of 3. And click on Find Services. So this is going to find all the services which has Gaia EDR3. We can take this one, which is, you can say Gaia EDR3 at ESA, or you can choose this one. You can choose any one if you want. And let us take an object. I'm going to take a star cluster.
Risha, sorry.
You're still Aladin screen?
Just the main
Okay.
TopCat.
Okay. Yeah,
Maybe
1 minute.
if you share all your screen.
Yeah, I'll do that. Yeah, I'll do entire screen. All right. I hope you all can see. Can you all see my TopCat now?
Now, yes.
Can you see the window also?
Yes.
Okay. So then I'll just repeat what I was doing. Please click on VO, which is for Virtual Observatory, and click on Cone Search. Okay, Cone Search. Here, please click on Gaia EDR3. Click on Find Services. You'll get many options over here. Choose the Gaia EDR3. And I'm going to write NGC 1960. This is a star cluster. Okay, please click on Resolve. In the radius term, just put it arc minute and just write 10 arc minutes. Okay, I'll repeat this next time, so don't worry in case you have a problem. And there's an OK button down. I hope you can see it. Yeah. So, oh God, I'm sorry. So please click on the OK button. And now you will see TopCat is directly accessing the data of Gaia. And here, if you click on table, you will see that this is showing you a table which has the array, deck, and various other parameters. I will continue on this in our next session, but essentially what I would like is you to try to install, right? I know I have only 3 minutes left, so I'm going to stop very soon. But I hope you used all these links which I showed you. Please try and install Aladin, try and install DS9, and install TopCat. Okay, these three things. We need to try to install Aladin, TopCat, and DS9. Okay, and the next session which I will have with you, which is on the 22nd, in day after tomorrow, we will be using all these three tools to actually study Gaia data. Okay, so we'll be doing an exercise using Gaia data using these tools. So I would request people who have attended today's session to try to install these three softwares. Try to install Aladin, DS9, and TopCat. And in case you have any doubts or questions about that, you can put that in the Discord. So in Discord, you can put it up, and I can see whether you have a problem in accessing, in installing any of that data. Because when we run it day after tomorrow, we would need to have all these things running on your system so that we can do the exercise, right? So I have a minute more, so I'll wind up and stop today. And we will meet 2 days, day after tomorrow. And we'll do an exercise using Gaia EDR3 data with all these softwares, right? So thanks a lot. Thanks for paying attention. And if you have any questions, you could ask, or let's see, I'll wind up because I think my time is up, right? Hello?
Yes, thank you very much, Prisha. There is some question here, or well, yes, we will start to move on the next.
Yeah. So in the Discord, on Discord, they can put up their
Yes.
question.
Oh,
So
okay.
so that by the time of our next session, everything should be running, right? So that they can do the exercise, right?
Okay. Thank you
Yeah.
very much.
Yeah.
I will
Thanks a
stop
lot.
recording.
Yes. Thank you.
Thank you very much. See you.